Hello guys, welcome to our machines class. It has been long since I last posted a video, but I know you guys are moving on to induction motors. But when I'm going to explain induction motors, I would want us to be online. So we will schedule a meeting probably later today so that we can explain what is really happening in induction motors. Because if I just make a video, we might have a lot of people that are going to have problems with it. But if we're online on MS Teams, there is no time limits on that one. So I'll be able to have enough time to explain. You can ask questions. I hope your network will be fine. And then I'm sure you will understand from there. So this small video is just gonna touch on power in three-phase systems. I know you wrote the tutorial and we had not touched on this, but it's pretty straightforward. So in power, remember power, we are basically talking about we have three forms of power. We have the real power, we have apparent power, and then we have what? Reactive power. So let's say, for example, in a three-phase system, we have a three-phase connected load, right? In that is connected in a delta. It's connected in a delta. In this manner. So let's make this one here, this line here R, and this one here blue, and this one here yellow. Right. So that means this point, okay, we have a blue here. This point from here to there, that's PR, right? Whatever we have here is PR. Whatever we have here is, what do you say? YR. And then what we have here is BY. BY. Okay, so let's say we have these loads, load 1, which might have an impedance Z. Now, let's say these impedances are balanced, which means they're equal. All right, so what happens is that when we have current flowing in this, let me just put the directions of the currents. The current here is flowing in this way. That's a phase current. Since it's balanced, our phase currents are going to be common. Another one is flowing this way, phase current also, and then the other one is flowing this way, phase current. Okay, so now when we have current flowing in this load here, now this load can be, we can say that this load is what? Can have inductance. That's why I'm saying this is an impedance. It can have inductance, it can have capacitance. It depends what your load is. So it will have some power factor where the current is now flowing in there. So then we will have power lost here. Okay. So now if I say that power lost, let's say that power is represented by power lost. Now talking about power lost, that is active power, represented by P. Is real power or active power, P. Let me just say P1 here. You will see that since the loads are balanced, that's the same power that will be lost here, which is also the same power that is lost here. So if you want to find the power in a three-phase, the total power that was supplied by our supplier in a three-phase system, that power, you need to find the power in each phase first. So the power in each phase is going to be V of that phase, I of that phase, and then also what else do we need? We need the power factor in that phase. we need the power factor. This is very important. We need the power factor in that case. All right. So once we have the power factor, and we all know that power factor is equal to cos theta. Ne? So I can rewrite this to be power is equal to V phase I phase cos theta. Simple. All right. So we take the phase quantities. V phase here also. Right. And now if you check, now this is only the power in one load. So the total power is going to be equal to 3, because there are 3 loads multiplied by the power in each phase. So that's going to be 3 Vp Ip cos theta. All right. So this is the total power. Let me just say Tp. Now this is expressed as per phase quantities. Now if I want it as in line quantities, using line quantities, if you check here, the voltage across BR is what we call the V line. Now if we check here, we have R, we have B. The phase voltage, you will see that in a delta connected system, the phase voltage is the same as what? The line voltage. So we know that V phase is equal to, just say V line is equal to V phase. Then the current, we have the line current here. Then we have the phase current there. Now we know that the line current, I line in a delta connected system, is equal to 3 root of 3 multiplied by the phase current. Okay, we already know that. So now what I'm gonna do is we are going to substitute. I just saw a squirrel here in my house. Okay. We are going to substitute here. Our phase current is going to be I line over 3. Therefore, now if we are going to express our power, our total power, I'm just having a lot of notations. Let's just use PT here. Okay, P total. We are going to have 3. V phase, we said, is the same as V line, so that one is just going to be V line. But in place of I phase, you're going to put I line over the root of 3. Then we have cos theta, right? Now if we simplify that, you see that root 3 into 3, that gives us a root 3. V line, I line, cos theta. That's our total power. Simple, straightforward. So that is active power. This is active power. Now, if you want to find apparent power, okay, my handwriting. Apparent power is simply S is equal to VI. Yes? Apparent power is the voltage times the current. Now, these we're talking about the magnitudes. So now, once you have your apparent power, now this is simple. We don't need to do much on this. Once you have your apparent power, remember the triangle, the power triangle. I have active power here, I have my reactive power there, then I have my apparent power there, then this is our phase angle. So your reactive power is going to be equal to the square root of apparent power squared minus the active power squared. So that is it in power. In power, the theory behind power in in three-phase systems. So let me just look at a question, because I know we wrote a quiz, but then this is going to be in the exam, so that's why I saw that it is important for us to look at it. So let me just look at one question. It seems I do not have my book for questions here. What I'll do is I'll create a question. Or we can take the one that you guys did in the quiz. Let's see. Let's look at the question. All right. So let's say we have a three-phase system. Now we have different loads. Load one is at is 30. Okay, let's not talk about the loads. Let's talk about the currents that are flowing. Right. Now, what is the phase current and the line currents? So we have a three-phase connected system. Ooh. This is our Y, this is our B, and this is our R. And you know why I put this one up there? Normally, the R is right here, and this is the Y, this is the B, right? But I always come and put the Y here because remember it's RYB, that's the notation. So let's say now here, we are given a line a voltage of 400 volts. And also here, that's only supposed to be in this way. I think so. Okay, we'll see. And here we also have 400 volts. So that's the line voltage. This one also 400 volts. Okay. Now we are told, let's say we are told that the phase current, the RB, BR, or RB, current that is flowing in this one, IRB, IRB, and then here IRY, and here IBY. So IBR, let's say we're given that is equal to 30 amps at an angle of 45 degrees. Or they can tell you, they can give it as a power factor there, perfect lagging, whatever. Then you're told that IBY is equal to let me just say 20 angle 30. Then IYR is negative what? Negative 15 degrees amps. The notation is what I'm worried about is normally, because I think YB is actually YB is common. YB, RB, and YR. Okay, it's fine. We'll see that. Let's just do the calculation. Okay, so these are the phase quantities. This one is the current flowing here. This one is the current flowing there, and this one is the current flowing here. So now here we have the supply current. Let's call it is the line current. So since it's coming in the R line, we just call it IR. And then here we have IB, and here we have IY. Right. Now the question would be, I know if I say find the line currents, that is simple because you're just going to take your KIL right here at these points. Okay? At these points. So that's how you would do this question. And what if the question is saying find the total power transferred? So remember the derivation I used was for a balanced load, but now as you can see, if you look at these values of currents here, you see that this is not a balanced load. This is not a balanced load. So there is the formula for total power is equal to √3 E phase V line I line cos theta. Will not work in this case because we have different what? We have different quantities. Let's just see how it goes. So let's calculate the line quantities. Let's calculate the line quantities just for the sake of interest. Let's see what happens. So the line quantities, if you take KIO about node R, you will see that you have the ones that are feeding into the node is IR, and IRY. Okay, minus IRB. Now that should give us a 0. So IR and IRB, this will be IRB minus IRY. These are phasor sums, eh? Okay, so IRB, now where is IRB? IRB is this one. No. Yes, IRB is this one. So it's gonna be a 30 angle 45 minus IRY, no, IYR. Yeah, the notation, eh? It's fine. That's a 15 angle negative 15 degrees. So now if we simplify that one, we change it to rectangular form, 30, 45, and we get radians. So I need to change this into degrees so that I won't have problems. Let me see. 30, 45. Okay, so I'm going to have a 21.21 plus, okay, obviously that's 45, so it will be the same, 21.21 minus, now I have 15, negative 15. Now I have 14.489. No, my calculator doesn't want to work. Okay, J 3.88. Okay, so let's simplify this. We'll get 21.21 minus 14.49, and we get 6.72. Anyway, 21.21 minus, that's becomes a plus 3.88. 88, we get plus 25.09. So if I now change this to polar form, 6.72 plus 25.09. Okay, polar 6.72, comma 25.09. You're gonna get a 25.97 angle 75 amps. So this is the line current in the red conductor. So you can calculate the line current in the yellow conductor, the line current in the blue conductor in the same way by taking these points here. Then you will see the values that you get. All right, so this was just a recap on calculating line currents. So you have an angle there. All right, but okay, we'll look at that. All right, so now we want to calculate, remember our goal is to calculate the power. So the power is if you can find the power per phase, let's say power in the phase BR, power loss in the phase BR. Power loss in the phase BR is going to be phase voltage, phase current, cos the angle between those two quantities. So what is the phase voltage here? And you can see that the phase voltage is the same as what? The line voltage. Yeah. The phase voltage there is the same as the line voltage. So so what we can do is that we just say it's equal to 400, right? The 400 multiplied by what is the phase current in there? It's 30 multiplied by cos the angle between those two is 45. So that is how you would work out this one. So it's there 400 times 30 cos 45. That will give us 8485.3 watts. But this is only for this part here. Let's calculate the power in the phase RY. Let's see power loss there. It's going to be the phase voltage, which is also 400 phase, line phase, cos theta per phase. So this is going to be 400. What is the current there? Current in the Y line, YR, that's a 15. Cos 15. So 400. I'm ignoring the negative sign. Even if I put a negative here, let me just put it. You will see that you get the same. Remember, cos is an even function. 15 times cos 15. This will give us a 579.55 watts. Then the power loss in the phase BY. Okay, this was RY. Is the same phase cos theta of that phase. So we're going to have 400, since it's the same, times the current now is 20 cos 30. That gives us 400 times 20 times cos 30. That gives us 6928.2 watts. So this is the power in each phase. So the total power, remember power real power can be added. You can edit. So I'm going to say the power in each phase. Power in the BR, power in the RY, plus power in the BY. Now if you add the 3, what you get is 8485.3 plus 5795.55. You get a 21,209. So this is the power transferred to the load, to our load. The total power that is gone to this load that was utilized by the load is that much. So that's a simple example that you can make on. You can look at other examples. Some of them are going to balance load. Now that one is easy because you just apply your formula straight away. √3 v line I line cos of the theta. Okay, since the theta will be the same for every phase. All right. So okay, have a good day. I'll talk to you guys later so that we can have a look at induction motor. I'll introduce to you so that you understand. That one is a bit tricky at first, but then you will understand it. So please be available. All right.